been a software developer for a long time, starting with APL many years ago, like some of the people in this room, and much more recently in 2013 getting involved with KDB+, working with projects related to the smart meter industry and utilities in general. And very recently, Affinity Systems was acquired by First Derivative, so we are now proud members of the FD group. When I got here earlier, actually, I was thinking the great thing about this venue is nobody's going to be able to hear us, which is really good. And then nobody will care either with this great bar here. And unfortunately, I managed to cure at least one of those problems. So I thought I'd begin tonight by talking about why you might want to profile an application in Q. My talk tonight is about profiling, but I thought I would just motivate why that's important. And I guess I could summarize it by saying perhaps that slow software sucks, which it does, but maybe it'd be more helpful to suggest that there's an important correlation between application performance and software success. These two are often linked together. Software that's responsive is generally more respected by its users, and it's usually perceived to be a time saver. And on the other hand, if you are working with a software application that's not responsive, that performs sluggishly, studies have shown that users tend to disengage, and they actually reduce the rate with which they respond to the application. So it slows down at both ends. So basically, the reason we profile an application is to gain an understanding of how it's working, to understand what it's doing and how it's spending its time, and use that information to help motivate, help inform decisions about how to optimize performance. At Affinity, we find that almost every application that we write has some kind of performance requirement, whether it's the need to generate a web page within some contracted period of time, or perhaps to execute and evaluate millions of events a second. Our philosophy is that software efficiency, like security considerations, really need to be considered at the forefront of the design phase of a project. And you need to have that pervade every aspect of the implementation right through to the completion of the project. Because if you don't do that, if you ignore performance constraints, you can end up building up an incredible technical debt that can take an embarrassingly long time to remediate at the end of the project, and may even require you to do significant software re-engineering. But even if you're careful about the way you write your code, it's important to be able to verify that software is performing as you expect from an execution perspective. And it's also important, if you chose to play with fire and ignore performance, to be able to zoom in on areas that require attention. So for both of these reasons, both to verify performance and to find the hotspots in an application, it's useful to have a profile as a tool at your disposal. From the show of hands earlier, most of the people in this room had some experience with Q, so you're going to be familiar with its intrinsic execution timing capabilities, which are \T and \TS. And these mechanisms basically provide a way to do micro-benchmarking of an application, such as you might do when you're, for example, trying to determine which of two competing expressions is preferable as you're building up a more complicated algorithm. Micro-benchmarking is really useful for looking at the performance characteristics of small sections of code, but often with synthetic approximations for things like input characteristics, timing conditions, and external events. Profiling, on the other hand, lets you take a step back and get a big picture of how an application is performing. By profiling it, you can get a sense of how the entire system is working, or at least how a representative subset of it is performing. And in that sense, get a macro perspective of where your execution time is going. But both micro-benchmarking and profiling have difficulties. It used to be possible to look at a piece of code, reason about how it was going to be performing, and be pretty accurate if you were to measure its performance. But that simplistic approach to doing execution analysis really doesn't work anymore. And the reason for that is because of the incredible number of abstraction layers that sit between the code you write and the actual impact that that code induces on the entire hardware and software platform. So to see what I mean, here, for example, is a picture of a microprocessor architecture block diagram. The code we write in a high-level language, or even in language like Q, which itself is compiled, and then the code we write is interpreted, ultimately gets get stored as low-level machine instructions. And the way that microprocessor architecture works is it fetches one instruction from memory, it decodes the instruction, it executes it in an arithmetic logic unit, and then the effects of that instruction cause changes to the CPU state and to registers and any memory addresses that need to be updated or modified. The only problem with this description is it's totally wrong. This is the way things used to work about 30 years ago. But nowadays, microprocessors are way more complicated than this. And the kind of machine that you would have in your notebook or your desktop or even in a server would be much more likely to look something like this. This is the microarchitecture of an Intel P6, which is pretty comparable to a state-of-the-art processor from AMD or from Intel. And it's got all the same components as the previous diagram did, but obviously a lot more. But aside from its obvious complexity compared to the way things used to be, there are a few words up here that should raise red flags to you. Words like cache, for example, which give the architecture the opportunity to make copies of data, programs, instructions, etc. in locations for its own convenience in order to improve performance. And that's a great thing. Some of these caches are very large, many, many megabytes. But the problem is it becomes difficult to predict where your code or where the data actually is, and thereby predict how it's going to perform. Other words like reorder, speculative, prediction. There's a myriad of stuff going on here. Modern microprocessors predict the execution path of your program based on what it's done recently. And you might think that having predicted the path, it's going to execute the instructions in the order in which they were written. That's not the case either. In fact, instructions are reordered for convenience of the processor to avoid CPU stalls. So the real order in which they get executed is going to be dependent on data relationships and also on instantaneous resource availability. And this whole picture really applies to just one core, but modern microprocessors have many cores, and often multiple chips. So there are signaling issues between the cores of a chip, between the cores of a processor, and across the processors that you have to take care of. So while it's not fair to say that execution is non-deterministic, it certainly is fair to recognize that it's opaque due to the anisotropic nature of so many of these fancy hardware architectural enhancements that have been made over the years. So however, even ignoring the hardware side of things, there's a lot going on the software side as well. As programmers, we actually owe somewhat of a debt of gratitude to the things we don't have to worry about in a high-level language. For example, if in Q, if we wanted to do a lookup in a table, we don't have to worry about how to implement that search. We can just depend on the fact that underneath the covers, Q is going to make some pretty intelligent decisions about which algorithm is most appropriate for it to use. And that decision will be made on things like the size of the data that we present, the data type of the arguments, and even spatial distribution of the data, and even the amount of free space available in the workspace, which Q may use for its convenience to create temporary data structures to optimize the search. So what I'd like to do actually is to give you an example show you an example of what I mean here. In a Q session, I'll do a simple micro benchmark, timing an expression 100 times, and I will do a lookup of an array within itself, and I'll make the array be 100,000 long, 100,000 long, and I'll take numbers 1, 2, and 90,000. And I'll do the search, and I'm getting two numbers back from TS. The first number is the number of milliseconds that this entire expression, 100 executions of it takes, and the second number is the amount of space that it took. So it's looking like it's taking about 140 milliseconds to do this, and it's taking 2 megabytes. But now, if I make one change to that line and multiply the last number by 10, you can see that now the CPU time has gone up by a factor of 6.5 or something, and the storage required has gone up by 2.5. So what's happened here is Q previously was looking at the density of the data and choosing a direct table lookup in order to do the search. Now, with the spread being much wider, it's picking a different data structure, probably a hash table or something like that. So while \TX provides a great way to do these kinds of micro benchmarks, it isn't really good for taking that step back and getting the big picture. And that's why we decided to take a look at building a profiling tool in Q. Now classically, when we think about profiling, there are basically three different ways you can collect the data. And there's a relationship between the way the data is collected and its impact on the processor, the accuracy of the data, and the amount of detail that we get from it. At one end of the spectrum, we can collect data by sampling. And the way that works is that you have an asynchronous timer that goes off every 100 microseconds or something, and it samples the processor's execution address and uses that as a proxy for what the machine's doing. Unfortunately, this sort of approach isn't going to work with an interpretive environment at all, so we can't use it in Q. The next type of profiling is a function level profiling, where we keep track of the entry and exits of functions, but without attribution of the CPU consumed within the function to the lines of that function. And the third type of profiling is line level, where we also keep track of the function entry and exit points. And in addition to that, we keep track of the boundary conditions between lines, and that way we can track the CPU to the actual line on which it occurred. Line level profiling stands the chance of having the most impact on the CPU, and it can really bring the machine to its knees if it isn't properly done. In fact, at Affinity, we've had experience profiling applications that were in Java or C++, pretty active financial applications, and doing line level profiles with tools that are out there brought the application to its knees, and we had to use a different approach. When we set out to build our profiler for Q, we had three basic goals. The first is we were looking for something that would be easy to use. Easy to enable profiling, easy to disable it, and easy to do that in a development context or production context. The second is we were really interested in profiling at the most detailed level we could, line level. And we wanted to be sure that we were incurring the lowest overhead possible. And finally, we wanted to produce something that was able to give us detailed reporting from which we could get actionable insights on how to improve the application. So what I'd like to do now is show you some examples of profiling in action. And I'll start with this pretty simple file, which is a pretty standard way to create a trade table. And in this particular case, the trade table is configured to consist of about 5 million trades taken from 1,000 unique symbols. So I'm going to load this file and execute each of its lines in Q. And we can see right here that something's certainly not going very well, because that took an awfully long time to run. Even without profiling, though, because of the simplistic way this file is written, each line being self-contained, I could actually use \TS to time every line. So let's do that, actually. I'll go ahead and prefix every line with \TS and then run. Oops. We're not. Sorry. Fix this. Apologies, it doesn't help that half of this is off my screen. Right, okay. This is going to take about the same length of time as it did to load the file, but I'll get a pair of numbers for each line, and those numbers will be just like the TS I did earlier. They'll be the CPU time consumed by the line and the amount of memory that it takes. So looking down here, you can see line 10 is consuming somewhat under 7,000 milliseconds, and that's the dominant portion of the time. The last line is consuming about 1/3 of a second, which isn't too bad. So now what I like to do is run this through the profiler. And the profiler that we designed actually profiles functions. It doesn't profile files. But if I look at this file, it's been written in such a way so that it has redundant semicolons at the end of every line. And so I can actually just string this together with new lines and use that to create a function. So I'll do that. I have to put the adornments around the function. I've got, as I expect, what I had in the file. Now, what I'll do is I'll load the profiler, which is in a file called prof.q, and the profiling functions are a namespace called prof. One of whose functions is called prof, and prof takes as its argument a list of functions or namespaces that are to be profiled. In this case, I'll just profile foo. Having done that, I'll execute foo. This is going to take about 7 seconds as it did before. And then I will run a report displaying what we got. So this report is showing us a few things. For every function that we profiled, which is just the one, it gives us the name of the function, the line number, the first few characters of the statement of the line, the number of times the line was executed, the total CPU time consumed on the line, including its subcalls, and the CPU time consumed on the line excluding its subcalls. So we can see from this that line 9, origin 0 of foo, so the 10th line of what we were looking at before, has been executed once, but is consuming almost all the time, 6,800 milliseconds, which is very comparable to what we got before. So let's take a look now at what this is doing. This is the line in question. And what it's trying to do actually is be a little bit intelligent about creating the prices at which trades occur. By instead of picking a random price for each of the 5 million trades, it picks a base price for each of the 1,000 symbols, and then randomizes the trade price based on the base. But the problem is it's actually doing work that is too proportional to the 5 million symbols. And that's unnecessary. What we can do instead of calling this code here on one symbol at a time 5 million times, we could actually rewrite it as follows. We can do a lookup in PS, and again, we'll do a lookup of the in the unique symbols against the same symbols that we would have created in the previous line, which is 5 million random symbols taken from the uniques. And we will add to that 5 million random numbers from 0 to 1. So this should be functionally equivalent to what we had. I'll save that file, go back over here, and I'll repeat the expression that computes the function foo. And I'll repeat the profile call to foo. And I'll repeat the run of foo. That ran a lot faster. And I'll repeat the report. And so now what we see is line 13, the trade insert line, is the one that's dominated, taking about 1/3 of a second. And line 9, that was so dominant before, is just a bit over 150 milliseconds. So that looks a whole lot better. Now, this is a pretty simple example, so I want to show you something a little bit more complicated. We've also written another package that does workspace searching of objects that are resident in memory. So for example, we can search for arbitrary strings within functions. And that package is called wus.q. So I'll load that, and I'll show you that in the package there's a function called funshow. And funshow takes as its first argument a list of namespaces or functions that are to be searched. In this case, I'll search the entire wus namespace. And its second argument is the strings that you're looking for. I'll just look for the string A. And when I do this, unfortunately some of this is scrolled off the top, but what we get is output that shows for each function in which a match occurred. It displays the line and then puts a caret underneath the A on the line. And you'll see A, of course, occurs in each, it occurs in value, and here A occurs as a variable all by itself. We have another function called SEShow, which does the same thing, but it filters its results syntactically. So the only matches that you're going to get are those that relate to variable names A or constants A that are not part of another expression. And when I do this, I get much less output as you would expect. All the A's in each and value are gone, and I just get the references to A as a variable. So now, let's profile the workspace searching package and see what we get. To do that, I'll profile the entire package, and I'll repeat this search for A that I did earlier. And I'll actually do the same sort of thing, but I'm going to add another string to it. I'll look for A, or the string FN. And here I get some more output. You can see at the very bottom here there are references to FN. This particular line actually has A and FN on it. And then I'll repeat that line syntactically. Okay, so now I've done 3 different runs, and I will now see what I got in the report. So unfortunately, this doesn't all fit on the screen. But one thing you'll see is that it actually still has references to foo from before. So let's get rid of that. I'll do an unprofile of foo and repeat the report. And now I get a little bit more succinct output that's just in relation to the workspace searching stuff. So we can see here at the top of the display is was.show. Line 0 was called 42 times, and it consumed 195 milliseconds. But actually, almost none of that was in that function. Almost all of it was in called functions. And the next thing is was.dippy line 5, which consumed 186 milliseconds. So that must be where all the time is going. So let's switch back over to the editor and take a look at the workspace searching routines. There's actually not much to them. We'll scroll down to Dippy. And this is line 5 of Dippy. This is the one that's the one that seems to be using most of the CPU. And it's actually not doing very much. What it's doing is for each line or every function in which there is a match, it's extracting that line and it's adding to it a line of blanks. And it's inserting into the blanks carets in the appropriate positions that will line up with that hits when they're displayed one on top of another. So there's nothing much here that we can really do to improve it, I think, except for the fact that, note at the very left edge here, we're actually outputting the results. And we might conjecture that maybe the performance issue is actually coming from the console. So let's delete that. We'll delete the -1 output to standard out. I've saved the file. I'll go back over here. I'll start with a clean slate by unprofiling everything. Now I'll load was.q again. I'll profile the entire namespace. And I will do those 3 searches again, which won't result in any output. I'll do the A, the fun show with the 2 strings, the SE show with the 2 strings, then I'll repeat the report. And now what we see is, as before, was.show is still being called 42 times, but now it only takes 12 milliseconds. And dippy line 5 is taking 2 milliseconds. So that clearly is the dominant part of the execution profile of this package. So I think you can get a sense here of how useful profiling can be to help you zoom in on where CPU is going, and in that way give you a good idea of where you should be making changes if you actually have performance problems. But it really is important to emphasize that you have to profile the section of code that's representative of what you're going to see in production. And you have to do it enough times to be sure that the results you get are not dominated by the hardware architectural issues that I mentioned earlier. In closing, I just wanted to say that the software is available on GitHub under Affinity Systems in the qprof package, and there is a link to it on the KX Systems GitHub page that Finn mentioned earlier. If you do use it and you have any feedback, we'd really love to hear it because we're very anxious to